Hello and welcome to episode 2 of our series Destination Mars.
Last time, we looked at what it takes to be an astronaut, but this week we're probing how would-be spacefarers will actually get to the red planet, battling against gravity, radiation and even sound waves.
And also news that scientists have grown the first kidneys from scratch in a Petri dish, news that vitamin pills can make cancer spread, and what a 4,500-year-old skeleton uncovered in a cave can reveal about our human origins.
I'm Kat Arney.
And I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
The Nobel Prizes in Chemistry, Physics and Medicine or Physiology have been announced this week. We've asked 3 scientists working in each of these 3 disciplines to tell us the stories of this year's winners and why their contributions have been so important. First up is Physiology or Medicine. Khalil Thurlaway is a parasitologist from Nottingham University.
Half of the prize goes to Chinese pharmacologist Tu Youyou, who discovered the antimalarial drug artemisinin by looking to the past for inspiration. She lived and worked in China during the Cultural Revolution of the 1960s and 70s, when intellectuals, including scientists, were looked down upon as a danger to the revolution. This changed, however, with the onset of the Vietnam War. China's ally, North Vietnam, asked the Chinese government for help because their troops were plagued by a particularly dangerous form of malaria, which was resistant to the standard drug at the time, chloroquine. People have already screened hundreds of thousands of potential new drugs to no avail, when Tu had the idea of searching back through ancient Chinese medical texts for possible cures. In a 1600-year-old text, she found a remedy which prescribed sweet wormwood for treatment of intermittent fevers, a classic sign of malaria. After refining the method, and even testing the drug on herself, she ended up with an effective cure for malaria which is still used today. It's called artemisinin, after the Latin name for sweet wormwood. The other half of the Nobel Prize is shared equally between William C. Campbell and Satoshi Omura for the parasite-killing drug ivermectin. Omura was working in Japan, searching for new antimicrobials in a group of soil-living bacteria called Streptomyces, which had already given us other medicines like the antibiotic streptomycin. He managed to isolate new strains of Streptomyces and grow them in his lab. Omura then sent the new bacteria to the USA for testing, where Campbell investigated their possible medical properties. He found that one extract from Streptomyces avermitilis was effective against a wide range of parasites in animals. He purified the active component and modified it to be safer and more effective. The resulting drug, ivermectin, is still one of the leading antiparasitic drugs on the market. In particular, it revolutionized the treatment of diseases caused by parasitic roundworms, which were a major problem in the developing world. Between them, ivermectin and artemisinin have saved millions of lives and freed millions more from lifelong disease burdens.
Khalil Thurlaway from Nottingham University with the story of the winners of the Medicine or Physiology Nobel Prize this week.
More on the other Nobel Prizes coming up later. But before that, for the first time, scientists from Australia have used stem cells to grow a new kidney in a dish. By controlling the conditions very carefully and adding a sequence of growth factors to fool the cells into thinking they're back inside a developing embryo so they turn into kidney tissue, Melissa Little and her colleagues have managed to create the closest equivalent yet to a real kidney.
You can take a stem cell and we can make that from any cell in anybody's body and actually convince that cell to go through the whole process as it would have in development to make a little kidney in a dish. The key is that many people have kidney disease and we really want to find a way of regenerating kidney tissue. And so we asked if stem cells could do this.
Why is it so difficult to persuade a stem cell to turn into an organ like a kidney?
You've really got to convince it to make the specific stem cells that form that organ. And the final kidney in an adult has more than 20 to 25 different types of cells, and they all have to be formed in the right place in the right time. So what we have to do is convince the cell that it's going through the normal processes it would go through during development. We've got to give it the right chemical signals. We've got to encourage the cells that are in there to talk to each other. And it's sort of like a recipe. You've got to add the right factors at the right time and give it the right amount of time. And then amazingly, the cells that form organise around each other to create the structure that we're looking for.
What did you start with and what did you end up with?
We started with a stem cell that was made from a skin fibroblast. So that's a cell that you can get from your skin. And then we added different factors in the dish. And it takes about 3 weeks. The stem cell will start to make choices. It turns into one cell type that becomes another cell type. And all of these are things that would normally happen in development. And then the cells talk to each other and form the structure that we see eventually. And so it ends up being about a half a centimetre to a centimetre across, with about 100 little tubes in it, with blood vessels forming in a very kind of complex little organ.
What's to stop you then growing, instead of something of that scale, a full-size kidney and then just plumbing it into an individual?
Technically, you should be able to make large numbers of these cells, but you can't keep structures that big alive without a blood supply, and we're doing this in a dish. So ultimately, it's got to be engineered so that we can provide it with a blood flow, and at the moment, it doesn't have one exit for the urine, which of course you've got to have because the urine's got to get out of your body somehow.
Can you surmount these problems of getting the blood supply and so on? Because at the moment this is in a Petri dish. How would one scale this to become a bigger kidney?
So can I just say it does have blood vessels, it just doesn't have blood flowing through it because it's got to have a source of blood from somewhere. So yes, there's a couple of ideas. Maybe if we just made large numbers of these cells and then put them back into a scaffold made from a kidney that's had all of its cells taken out, or actually bioprint a structure of some sort. I guess we have in our heads this idea that you've got to build something as big as what you're replacing. But dialysis, which is what a lot of kidney disease patients live on, only gives you 10% kidney function. So there's a lot of room for improvement over that.
And how do you know that what you've created will actually work? How do you know this is functional tissue?
We have tested some functions. Obviously, they don't make urine because you can't make urine unless you've got a force of blood flowing through your structure, and this is in a dish. But we have asked things like, are the cells in the organ starting to do some of the other functions that they normally do? For example, we've asked, there are some drugs that are actually really toxic to the kidney, and so we've put on those drugs and said, am I seeing this specific toxicity to that drug? And these kidneys are responding the way they would in an animal or in a human.
You've therefore created not just a potential platform from which we can, in the future, develop full-size kidneys, but also quite a useful test vehicle for actually trying out drugs in future.
Yes, and I think that's actually very short-term future. We hope to be doing this very shortly. And it's not just using these as a little model of an organ to test for whether a drug is toxic. We can actually make a mini kidney basically to order. There are many patients out there with kidney disease that have mutations. We can make a stem cell from them. We can build a model of their kidney in a dish and actually use it to understand their disease and maybe develop treatments that are more tailored for their kidney disease.
Incredible work, isn't it? Melissa Little, she's from the Murdoch Children's Research Institute based in Melbourne, and that work was announced this week in the magazine Nature. You're listening to The Naked Scientist with Chris Smith and also with Kat Arney.
Still to come, Destination Mars. If we're going to colonise the red planet, how on earth will we manage to make the 9-month journey, battling against the perils of space? And I don't mean aliens. Plus, how some vitamins might make cancer more likely to spread. Stay tuned to find out how.
Before that, continuing with our look at this year's Nobel Prizes, here's Bath University chemist Emma Sackville.
This year, the Nobel Prize for Chemistry was jointly awarded to Thomas Lindahl, Paul Modrich and Aziz Sankar for their work into the mechanisms by which cells repair damaged DNA. Up till the early 1970s, many people believed that DNA was a stable molecule. However, Thomas Lindahl showed that DNA is damaged at such a high rate that life should be impossible. It was this discovery which led him to conclude that cells must be able to repair that damaged DNA, and this in turn led him to identify one of the ways that cells can do this, in a mechanism known as base excision repair. Our second Nobel laureate, Aziz Sankar, was first drawn to repair mechanisms by his interest in how UV-damaged bacterial cells can regenerate when illuminated with blue light. This seemingly magical occurrence eventually led to his discovery of a mechanism called nucleotide excision repair, which repairs DNA after a cell has been exposed to UV radiation. As well as damage from radiation and its inherent instability, errors in DNA can also be generated during replication. This is the process by which cells copy their DNA message, and it happens millions of times a day in your body. Paul Modrich, who shares the prize money of 8 million Swedish krona, was instrumental in identifying the exact proteins responsible for so-called mismatch repair, which can correct 99.9% of all replication errors. The detailed understanding which these scientists have uncovered has implications for cancer research, as well as in expanding our knowledge of hereditary diseases, hopefully bringing us one step closer to treating them.
Incredibly exciting news. I actually work for Cancer Research UK and Thomas Lindahl is one of our Nobel Prize winners, so very exciting day in the office. That's Emma Sackville. She's a PhD student at Bath University's Department of Chemistry.
The Physics Nobel still to come here on The Naked Scientist. Well, it's time to look backwards in time now, because this week scientists at the University of Cambridge have successfully sequenced the genome of a 4,500-year-old human who was uncovered recently in Ethiopia. The results reveal how our early ancestors migrated out of and then back into Africa. Andrea Manica is one of the team who did the work. Where did you find this gentleman? Because you sequenced him. He's called Motta, isn't he?
It's called Motta indeed. There's a gentleman that lived 4,500 years ago in the southern part of the Ethiopian highlands. He was definitely a hunter-gatherer, and we found him in a cave that actually was already in use about 5,000 years ago, and then it was continuously used through time out to about 2,000 years ago, as we saw people going from hunter-gatherers to pastoralists and to started producing their food.
Why was he in the cave? Had he died there?
He was actually buried there, so we find him buried face down, probably bound as they used to do at a time, with some of his tools they would have used for hunting next to him.
Quite a dramatic finding. And how did you manage to get DNA out of him? Because I would think that's quite a contaminated site, isn't it?
Actually, he was under a very good layer of rock, so we managed to recover his remains as pretty much untouched. And we're already at the time working with the archaeologists, so we managed to get really nice, clean found.
And where did you get the DNA from? What part of his body?
We managed to get it out of what is called the petrous bone, which is this little bone that is behind your earlobe. It's just really hard and it preserves DNA really well. It just doesn't get the bacteria coming in and destroying the DNA.
How did you read the sequence?
Well, we managed to sequence the whole genome, so we actually got a complete blueprint, and then we were able at that point to really compare it to other Africans as well as other genomes from the rest of the world.
Why is this important in our understanding of modern humans, i.e. us, and where we came from?
Well, we came out of Africa, as you mentioned before, about 50, 60,000 years ago, but we started having some inkling over the last few years looking at modern Africans that Western Eurasians might have actually come back in numbers into Africa about 3,000 years ago. So Motta, by living 4,500 years ago, lived just before that time. So it gives us a really nice reference for what people looked like before this wave.
If one therefore looks at present-day Africans and looks at their genome, have you got evidence in modern-day Africans then of, I don't want to use the word contamination, but their genome is stuffed full of genes mixed in from people who went out of Africa 50, 60,000 years ago, lived in Europe for a while, evolved there for a while, and then came back into Africa and bred with those Africans again?
We do. We don't quite know whether they made it all the way into Europe proper, or maybe they just stopped around the Near East, Anatolia. But yes, we were quite surprised because even the furthest corners of Africa, like Western Africa or South Africa, actually have about 5% of their genome dating back to this wave of Western Eurasians.
This individual is in Ethiopia. It's quite high, that area. The best marathon runners in the world come from Ethiopia because they've got these genes that give them adaptation to tolerate those low oxygen conditions. Is the same true of this gentleman, Motta?
It is indeed. It actually has those key adaptations that we found in Ethiopians right now. They were already there 4,500 years ago, and probably they'd already been there for a long time. These were people who had to deal with this complex environment. They were hunter-gatherers. They had to chase down their prey at those altitudes. They were highly adapted to that life.
And now you have the sequence from Motta. What are you going to be able to do with it, which is going to change our understanding of those migration patterns?
Well, every time we try to reconstruct what happened to humans as they came out of Africa, analysis, for example, of hybridization with Neanderthal during that time of
mixing in
with Neanderthal, we always have to use an African reference. And until now, we always use these modern Africans as our references. So, for example, in the case of the mixing with Neanderthals, we're actually missing some of the mixing that happened because our reference was already, as you were saying before, a little bit contaminated, or at least already contain some of that those Neanderthal genes.
So you finally got upstream of all of it. Super. Thank you very much. That's Andrea Manica, a researcher from Cambridge University who sequenced a 4,500-year-old Ethiopian.
New research has shown that taking antioxidant vitamin pills after a cancer diagnosis might increase the chances of the disease spreading. Antioxidants like beta-carotene and vitamin E were believed to help protect our DNA from damage and reduce the risk of cancer. But clinical trials of antioxidant supplements suggest that, in fact, they might have the opposite effect and increase the chances of dying from the disease. A new study on mice with the skin cancer melanoma by Martin Burgo from the University of Gothenburg in Sweden helps to explain why.
Well, first we studied what happens when we gave the antioxidants to the mice that already had small tumors on their skin. So we gave them an antioxidant in the drinking water, and at first we were surprised because we didn't see any effect on the primary tumor. The number and sizes of primary tumors were unaffected. But then when we looked inside, it turned out that the antioxidant supplementations had doubled the frequency of metastasis.
So that's cancer spreading through the body?
Yes, exactly. And that's really the most dangerous part of most cancers' progression, and particularly so for malignant melanoma.
What do you think your results might mean for patients? Obviously, this is an animal study, but are there lessons that we can take, or is it a bit soon to say?
I don't think it's soon to say. I mean, first thing we did after we found this in the mice is that we looked at a large panel of human malignant melanoma cell lines, and we found the same thing there, even when they were cultured, that the proliferation of these cells, or their ability to divide, did not differ when you gave them antioxidants. And that's in analogy to the primary tumor not being affected in the mice. But then their ability to migrate and invade tissues was increased by antioxidants. So this actually happens in human cells also.
How are the antioxidants having this effect? It seems a bit strange that something like that could be encouraging cells to grow and invade more.
I think the simplest way to put it is that antioxidants can protect healthy cells from free radicals, but they can also protect tumor cells from free radicals. And free radicals can limit a tumor cell's ability to proliferate, and free radicals can limit the ability of malignant melanoma cells to metastasize. So the antioxidant is helping the tumor cell.
Is there a message for cancer patients from this research, perhaps if they're seeing adverts for antioxidants or reading about them on the internet?
This is something that is very important to debate at this point. Research is showing that people who have just been diagnosed with cancer are more prone to take antioxidant supplements than the general population. So this is very important that they find out potential risks of that. It's time to perhaps draw some general recommendations from that and suggest that cancer patients should not supplement their diet with antioxidants.
We do hear a lot about naturally occurring antioxidants in fruit and veg and things like that. I mean, does this mean that people shouldn't eat their 5 a day or avoid fruit and vegetables?
That's a very good question. And it's important to note that we have studied antioxidant supplementation, and we have chosen doses that you would be expected to get as a human if you were taking a supplement, a pill. But it's not excessive doses. You wouldn't have to take a lot of those pills. You would have to take a normal dose of an antioxidant supplement. So there's no reason, at least from our studies, to suggest that antioxidants in the food would cause this effect.
So eat your 5 a day and save your money on the vitamin pills. That was Martin Burgo. He's from the University of Gothenburg in Sweden, and that study came out this week in the journal Science Translational Medicine.
Back to the Nobel Prizes now, and University College London's Andrew Pontzen.
The Nobel Prize in Physics has this week been awarded to particle physicists Takaaki Kajita and Arthur MacDonald. So, for those of us who haven't yet managed to get that winning phone call from Sweden, what should we learn from this announcement? First, be patient. The work that's been rewarded this week was mainly carried out 20 years ago, and it was all about working out what's going on with neutrinos, little tiny bundles of energy that are incredibly hard to detect. The existence of neutrinos had been predicted in the 1930s to make sense of nuclear reactions, but they weren't actually first detected until 20 years later in the 1950s. And the Nobel Prize Committee finally got around to rewarding just that very first detection a full 40 years later in the 1990s. Second, it's great to be competitive. The work being recognised by this prize was carried out by two completely separate teams, because Takaaki Kajita's team worked on the Super Kamiokande experiment in Japan and reckoned the best way to study neutrinos was to use the stream of them produced by cosmic rays striking the Earth's atmosphere, whereas Arthur McDonald's team were working on the Sudbury Neutrino Observatory in Canada, which instead was studying neutrinos naturally produced by the nuclear reactions in the Sun. Both experiments saw hints that neutrinos suffer from a bit of an identity crisis. There are actually supposed to be 3 different types of neutrino, but the results from the 2 experiments only made sense if each neutrino changes its mind from time to time as to what type it is. So at any given moment you could say, okay, this neutrino is an electron neutrino, but you look again and after a while it's turned into a tau neutrino. It's all very strange, and so it's the kind of thing that you wouldn't really believe from one experiment alone. But the real lesson is to make sure that you're the boss. These are complicated experiments. The papers announcing the discoveries have around 200 authors on them, but only the boss from each team has been recognised. So even if you are involved in the next Nobel-winning discovery, chances are it won't actually be you getting the prize.
Doesn't seem very fair to me, does it? That's Andrew Ponson from UCL.
And you're listening to The Naked Scientists with me, Chris Smith.
And with me, Kat Arney. This month, we're launching a series of programmes that will probe what it's going to take to send people to the Red Planet. Previously, we've looked at what it takes to be an astronaut, but this week we're focusing on the journey. How will we get to Mars?
To rocket engineers, just the idea of transporting humans to Mars is a really serious headache. Compared to rovers and other inert satellites and probes, humans are highly unpredictable, needy and fragile things. Radiation is our body's kryptonite. Microgravity renders our bones thin and weak, and if you broke a leg, for example, it could take months to fix. Now, these are just a few of the hundreds of problems that scientists are grappling with when they're considering how they might send people to the rocky red planet.
Greer Jackson ventured to the Mars Yard at Airbus Defence to meet Paul Meacham to uncover exactly what we're up against.
Mars is not the easiest place to get to. I mean, it's actually very demanding. Even just getting off the surface of the Earth is difficult because our gravity, it doesn't feel very strong to us, but it is an incredible force to overcome.
And then getting there, I imagine, it's 9 months?
It is a very long time, yes. 9 months in cruise. And of course, during that whole time, you're away from the Earth's protective layer. So you're subject to the full elements of space. It's quite tricky to overcome that.
You've got a big job on your hands then.
We certainly do, and that's why facilities like the Mars Yard are so important, because it allows us to practice everything we're going to need to worry about when we get to Mars on Earth.
This is the weirdest place I've ever been. I don't know quite how to describe it. Lost for words I was, but imagine a giant sandpit filled with, bright orange sand and a mixture of real rocks and polystyrene boulders. Taped to the walls were vistas of Mars. Bar the lack of weightlessness, the scorching effects of radiation, and the bountiful levels of oxygen, I did feel like I was traipsing around Mars. This is the Mars Yard, and no, it isn't a film set. It's where scientists like Paul test out prototypes of the ExoMars rover, which will be sent to the Red Planet in 2018 for more scientific tests. The latest prototype is rather fondly referred to as Bruno.
Bruno has on him all the sensors the real rover will need to drive itself autonomously. That's the cameras and all the sensors in the wheels and that sort of thing. So essentially we practice driving the rover by itself in this Mars Yard.
Can we take her out for a... him. Can we take him out for a spin?
Yes, we certainly can. Yes.
Am I allowed to tread on the sand?
You can.
And away Bruno goes. Bruno looks like a giraffe. Instead of 4 legs, he has 6 wheels, and the wheels resemble the sort of things you get on tanks. What strikes me is there is a huge number of things to consider here and a huge number of things that could potentially go wrong. And this is just a rover that's, about my height roughly. What about when we're sending humans to Mars?
You've got to think about all the elements that the human is going to have to withstand and try and protect them as much as you can from it. So one of the easiest examples is the launch phase. So if you're strapped on top of a rocket, it's not a very pleasant place to be. You are getting blasted with lots of vibrations, lots of sound waves. So you've got to build your spacecraft to be able to withstand all those forces and not transmit too many of them to the actual passengers.
How do you test that?
Essentially, you've got environmental test facilities where you have a big table that shakes the spacecraft. We even have a room where we do acoustic test. So essentially we stick the spacecraft in there and we blast it with sound waves. It's not a particularly pleasant place to be, because if you were a person in that room when we were testing one of our spacecraft, you would be killed.
Death by sound waves doesn't sound like a nice way to go, and that's just the takeoff. So what's next? What else have you got to think about when you get out of the Earth's atmosphere and into space?
Probably the main consideration is the radiation environment. As you say, we're leaving the protection of the Earth's atmosphere, and you are then subject to the full force of solar wind and cosmic radiation. We're well aware of the effect of radiation on the human body. It does not do nice things, and you've got to fly through that for 9 months.
I'm assuming that's a huge concern, because I know when on the Apollo missions that something like 3 days in space was the equivalent of 12 chest x-rays.
That's right. They flew through what we call the Van Allen belts, which are belts of radiation that surround the Earth. It's a particularly high-energy environment. But yes, as you say, that was only 3 days, and we're talking 9 months. So the equivalent dose is much, much higher, and so we're going to have to think about ways to protect the astronauts from that.
So we're in space. We're now protected somehow against the radiation. Mm-hmm. What else are we battling against?
The next thing to think about is actually keeping your astronauts alive, because you've got to take everything with them that they are going to need. Most essentially is oxygen, but oxygen is not a particularly pleasant gas. It's extremely flammable, so you've got to think about how you're going to store that very carefully. The famous Apollo 13 mission was caused by an exploding oxygen tank, and it caused serious problems. And at least in that case, they had half a chance of getting back to Earth, whereas if you're halfway to Mars and that happens, you have no chance of return at all.
If we do eventually overcome all these perils, what have we got to worry about when we're coming into the surface of landing?
Primarily, it's going to be the temperature range we're going to experience. So we have to qualify most things on the outside of our rover for temperatures between minus 130 degrees centigrade up to about 55. So you're going to have to create an environment which is around room temperature and can withstand these massive temperature extremes we see on the planet. And that's not easy to do.
No, quite. Do you have faith in your colleagues to engineer something clever that can do all these incredible things?
Yes, because I think we'd use something which is not dissimilar from what we use on the inside of the rover. The rover's main structure is called a bathtub, and it has the space equivalent of double glazing in order to create a thermal barrier through which heat can't get in and heat can't get out. And then when you do that, you can create quite a habitable microenvironment within that cocoon.
So our astronauts are going to be living in bathtubs?
Well, I shouldn't have called it a bathtub, should I? That's what we refer to the main structure of the rover.
Fantastic. Paul Meacham from Airbus Defence. And as Paul pointed out, one of the biggest obstacles we've got to overcome is cosmic radiation. How will we protect the astronauts on board from these potentially deadly rays?
Well, Ruth Bamford from the Rutherford Appleton Laboratory in Oxfordshire thinks that she might have the answer. It's not actually all that dissimilar to how the Earth protects us at the moment from radiation. Ruth, just define for us, first of all, though, what actually is cosmic radiation?
Out in space, there are lots of small particles that are accelerated at very high energies and can penetrate deep within the body and cause lots of damage.
What sorts of particles are there? What are they called?
Well, they're protons and electrons, the substance of the sun, and they're accelerated by the explosions on the sun.
I suppose then that you get these particles there going at very high energies, and given that they're very small, they're capable of penetrating the skin of, say, your spacecraft. And then if you happen to be in the way, they're going to go through your body, and they could well interact with the cells in your body and act a bit like a microscopic missile.
Yes, that's exactly right. They go through the hull of the spaceship, and then they're able to penetrate deep inside the body, just like microscopic bullets, and can damage nerve tissue and cells and cause organ failure, ultimately, if they're in very high numbers.
Are you saying then that it's not such a risk of getting cancer because of damage to your DNA that you might not even live long enough to get cancer. If you had a big dose of these things, they could just wreck your cells in all your tissues and make you acutely unwell just during your space journey.
Yes, that's right. They reckon that the general quiet time solar wind is sufficiently low for you to be able to survive a trip to Mars, as long as there isn't a big storm that produces a large number of particles at very high energies. And if that happens, the human body can't deal with it, and you get acutely sick and potentially could die, but even acutely sick is threatening for the entire crew to be in that state.
Obviously, we can't take that chance. We want to come up with some kind of way of dealing with this. But given that the Earth is effectively a spacecraft, it's in orbit around the Sun, the Earth must be being hit with these streams of particles all the time. So why aren't we seeing them here at the surface?
We do see a small fraction of them, but we have a couple of lines of defence, the first of which is the Earth's magnetic field that helps to slow down the particles and deflect a lot of them. And then after that, we've got the Earth's atmosphere, which does a good job of cutting out a good fraction of the particles that otherwise would hit us.
What about when we put things into space then? If you look at the International Space Station, for example, are the astronauts there subject to more radiation?
The astronauts on the International Space Station encounter about 200 times the radiation we do on the ground, but the space station is still within the Earth's atmosphere, right at the edge, so they are still partly protected by the Earth's magnetic field. But even so, they do have like a panic room, which they have had to use on occasion when there have been big storms.
And such a room wouldn't be practical for our craft that we want to send to Mars?
I'd expect that a Mars ship would have an extra shielded room, but it can be because you don't have the Earth's magnetic field and the magnetosphere protecting you, that the energy of the particles you're encountering will go through that, because we believe it goes through meters of concrete.
So that being the case, what approach can we take then in order to protect our astronauts so that if there is a storm, they're not fried in their spacecraft?
Well, what we'd like to do is take a leaf out of Nature's book and try and put an artificial magnetosphere around the spacecraft.
How do you intend to make the field?
What we'd expect to do is make a very large loop of superconducting material and energize that if it's needed for a storm, using the power that the rest of the time is being used to power the spacecraft systems.
I see. And you use the fact that you have a coil to create the field you need?
Yes, that's right.
And how strong would the field need to be? Because that doesn't sound like a very big solution. It sounds pretty simple, really.
Well, it's simple in concept, but in fact the interaction is immensely complicated. From our study, it's looking much more credible level of power for a manned spacecraft. So you're talking about a few Tesla for a magnetic field.
And to put that into perspective, that's sort of roughly on par with the intensity that you get in a hospital MRI machine, isn't it?
It's even less.
And once you create that field, what does it then do to the spacecraft in order to mean that these particles, with formerly the ability to penetrate meters of concrete, are suddenly tamed?
Well, the magnetic field acts on the two charges in the solar wind. You have your negatively charged electrons, which are very light, and your positively charged protons, which are the hazard that you're concerned about. So a magnetic field will pick up the electrons very quickly and redirect them because they're so light. And the ions, the protons, would normally find it quite difficult to follow the magnetic field lines. But they notice if they've lost their electrons, because that sets up a space charge, an electric field. And it is that electric field that then pulls back on the ions and will redirect them, hopefully, away from the spacecraft.
One therefore thinks that were you to transplant this approach to an interplanetary vessel, it could work.
We're very hopeful that it could.
Well, we'll just have to watch this space then. Thank you very much. That's Ruth Bamford from the Rutherford Appleton Laboratory. You're listening to The Naked Scientist with Chris Smith and also with Kat Arney.
Now that we can check radiation off our list of things to worry about, we can turn to the daily grind. What's life in space like for an astronaut? How do they eat? How do they sleep? And what about showering and all the other bathroom stuff? How will they survive the 9-month journey? NASA astronaut Stanley G. Love took Greer Jackson through his time in space, starting with takeoff.
9731 left, left Bravo, right Juliet, close short of Zulu.
You get strapped in 2.5 to 3 hours before you launch. So you have plenty of time to think about whether that was really a good idea.
What was going through your mind?
Well, the usual two sort of astronauts' prayers were the standard one is, I really hope I don't screw up. And not everybody admits it, but many people are also hoping they don't get blown up.
6, 5, 4, 3, 2, 1.
Launching from the ground to reaching orbit takes about 8 minutes. And during that time, there are milestones that you're sort of checking off, places where you say, okay, from this point on, if we lose an engine, we're going to fly across the Atlantic and land in Africa, whereas before that, if we'd lost an engine, we would have tried to turn around and land back in Florida. There was also a milestone that my commander read off to us over the headsets. He made a little congratulatory statement for us rookies on board, congratulating us on making it to space and officially becoming astronauts. And when the engine's cut off and you're floating in orbit, that's 40% of the risk of your entire space mission has just been retired in those 8 minutes. So you get a good feeling thinking, this just got about twice as safe as it used to be when I was sitting on the pad 8 minutes ago. So that's a great feeling. Floating in your straps is just amazing. And then the next thought to hit you is, it is now time to get to work.
Paint me a picture of life in space. I imagine microgravity plays havoc on all sorts of things in terms of how you sleep, but also how you eat and shower and all that sort of thing.
Shower? Who said anything about showers?
Oh, blimey. 2 weeks without a shower?
Well, imagine turning off the gravity and turning on the shower. Water would go flying everywhere. So if you want to take a bath, it's going to be a sponge bath. But you're right. Daily life really has a lot of changes when you're in microgravity, especially at first when it's disorienting. I mean, there's a few fun aspects, especially after a couple of days you get used to it. So you can actually put your pants on both legs at the same time in microgravity. But getting into bed, setting up a bed, takes a long time. You're setting up a sleeping bag, basically, that's attached to the wall or the floor or the ceiling, if you like. Changing clothes is hard. Eating is hard. Most of our foods are in sort of packets, and you kind of cut open a corner and kind of nibble, or if it's a liquid stuff, you can kind of suck the contents out. But it just takes a long time to get anything done. Going to the bathroom can take half an hour, especially the first couple of times. The biggest surprise on the whole flight for me was not during the flight, but after landing. As your system gets used to being in gravity again, you can be very dizzy, like your head spinning. And I didn't quite expect that. I expected some of the other effects to feel kind of weak, maybe sick to my stomach. I did not expect to be dizzy. But in general, we were very, very well prepared for our flight. And folks who had been there came back and told us about their experiences, so there were not very many surprises.
You're mentioning the effects of microgravity there, and there's lots of talk about the effects on bone density and muscle wastage. Was this something you encountered after 2 weeks when you returned back to Earth?
Absolutely, but I was a bad astronaut and I did not do my exercise. But I had ample time to regret that when I came home. So I lost 8 pounds of muscle, almost all out of my legs. If I went again, I would not blow off my exercise because it made a huge difference. And that was only 2 weeks. You can imagine if you were up there for 12 times longer than that, being up there for 6 months.
How long did it take you to recover those 8 pounds of muscle?
Several months. I have this memory of being finished with the spacewalk, waiting outside the airlock to come back inside, and our shuttle's orbit took us up over the Pacific Ocean and across the western part of the United States, and just having that immense tableau of scenery of all the world that I'd known growing up, and having that just come rolling up underneath me as we were finishing that spacewalk and feeling good about it. That was a wonderful, wonderful experience, and something I'll remember for the rest of my life.
It sounds beautiful.
It is. I like to say, and this is a strong statement coming from somebody with a background in astronomy, that the Earth is the most interesting thing in space. So I'm hoping that in the future more and more people can see what it's like to be in orbit, look down at the Earth, see what it really looks like, and observe our home as a planet rather than just as something you drive around to work and back every day. And I think it will make us all better people to have that experience.
One of my lifelong dreams to go and see that. That was NASA astronaut Stanley G. Love. And it's actually worrying to hear, isn't it, how much muscle he managed to lose in 2 weeks, isn't it? Yet alone being out there on a spacecraft for 9 months going to Mars. So could living without gravity be a major concern for our would-be Mars-bound astronauts?
Well, to answer this question, we are now joined by Mark Wilson. He's a neurosurgeon who thinks a long-haul trip to the planet could have some serious, but not insurmountable, health effects. Hi, Mark. So we've heard about how Stanley came back with some loss of his muscle mass, but what about some of the other effects?
There are many effects. My area of research is what happens to the brain in microgravity and in hypoxia. And what happens is that because you haven't got gravity pulling blood into your legs, you get this fluid shift, and we think that the intracranial pressure rises. Now, what's happening, we're finding in longer space missions now, the chronic changes that are occurring are actually causing another phenomenon which is known as VIP, visual impairment intracranial pressure in space, where the astronauts are losing peripheral vision. And this is also a long-term problem that could be an issue in a mission such as one to Mars.
Basically, all their blood's kind of going into their head and the fluid's got to go somewhere.
Yeah, I think what's happening is that you've got this reduced ability to drain venous blood. And if you're sitting here now, you're putting about a litre of blood into your head every minute, and a litre of blood has to get out every minute as well. And when you've not got gravity helping that, you can't drain blood quick enough.
So that's what's going on at the head end. So what about further down, the rest of the body, the skeleton and the muscles? How does this low gravity environment of a spaceship affect them? What's going on at a physiological level?
Well, because they aren't exercising in a normal way, and by that I mean when you normally exercise, you're walking or you're running, you have constant impact exercise. That's what helps bone turn over effectively. Because they haven't got that, they lose bone mineral density. And the other thing they haven't got is gravity pulling blood into the tissues. So even when the people have exercised in space, for example, just running on a treadmill with braces to hold them on it, they still lose bone mineral density and muscle mass, because although they have impact exercise, they haven't got the gravitational force pulling blood into their legs. So those are the two things. It's blood flow and impact exercise that are required to maintain bone mineral density and muscle mass.
I mean, how does this affect the body? Because presumably if things like muscle and bone are starting to break down, the components of those have to go somewhere.
Yeah, and you gradually excrete the protein out, and you gradually lose the calcium. Although it does differ in different parts of your body. So the work that I was previously involved with was looking at what happens to your head more than anything else. And your cranium actually tends to deposit more bone rather than lose it. So it's not all loss. It's depending on where it is in your body that's changing.
So, for example, on our hypothetical 9-month trip to the Red Planet, going to Mars, we've already heard that just after a reasonably short trip into space, Stanley Love, he lost about 8 pounds of muscle. How much would the average astronaut expect to lose?
Well, there's different studies, but on average, the studies seem to show that people lose between 1% and 5% of their bone mineral density per month, that is, during microgravity. That's quite a lot if you're going to be spending 9 months travelling somewhere. We don't know whether it plateaus off, and some of the evidence from the International Space Station suggests that it does, but if it's not going to plateau off, then obviously you're going to have quite a lot of loss before you arrive.
I mean, you can almost imagine, is someone just going to basically turn into a jellyfish? What would be the ultimate end point for this?
We don't really know, but it's not really the fact that they might have a little bit of loss that will be okay. It's more if there's an emergency situation when they arrive at wherever they're going. You need to be able to maintain bone mineral density and muscle mass that you can run away or move and do the appropriate things, even in a relatively reduced gravitational environment. So from a safety point of view, although people say, well, if it's a one-way trip, does it matter or something like that? It does matter, because actually you may well need to be able to do stuff when you get there.
So, for example, just getting down from your rocket onto the surface of Mars, would there be a risk if you tripped and fell over, you would just snap a bone like that?
We don't really know, but that is a perceivable risk. And there's been a lot of work looking at countermeasures to try and minimise this bone mineral density and muscle mass changes.
So what sort of things have you looked at? What sort of approaches can people take?
Well, I mean, and if you look at the old Space Lab missions and some of the stuff from the 80s and 90s, people used to exercise in space with braces over their shoulders, holding them onto a treadmill. And that didn't really prevent bone mineral density and muscle mass changes, because although you're getting the impact of exercise again, because you haven't got blood being pulled into your legs, you still lost bone mineral density and muscle mass. So some of the countermeasures that are now being suggested as things like lower body negative pressure, where you sit in a chamber that sucks air out from around your legs, as well as having a treadmill on the bottom, and then you've got effectively an artificial gravitational force across you pulling blood into your legs, and you've got impact stress, and that seems to prevent bone mineral density and muscle mass changes. The problems with that is it requires a bit of power and also constant vibrations, which would affect things such as crystal experiments or other stuff that might be going on. And then there's other measures such as interlimb resistance devices, where you use one leg as a resistance device against the other. There's things such as human-powered centrifuges, where effectively two bikes are set opposite each other, and by exercising against each other you can create a gravitational force that as you spin round. But all these are quite big things, and if you've got a relatively small small craft during such a mission, it's going to be difficult to plan it into that. So there's lots of work going on in this area.
What about things like drugs? And I'm sure I remember seeing a study about looking at how bears hibernate, because they lose their muscle mass when they hibernate, but then they kind of get better again. What could we learn about maybe tweaking physiology with drugs or chemicals to help reduce these side effects?
Well, it's interesting you say when bears hibernate rather. It's lying down. Even if you just lie down for a prolonged period, you lose bone mineral density and muscle mass. So it happens in humans as well. And we don't really know enough at the moment in terms of whether we can optimize things with hormonal treatments or with additional calcium and vitamin D and things like that. It does seem to be that really to maintain bone mineral density and muscle mass, you have to be using them. And so whilst drugs might offer a small benefit, it's unlikely to be the sole solution.
So use it or lose it, at least for now. That's Mark Wilson. He's a neurosurgeon and space physiology researcher from Imperial College London.
Now, when it comes to landing on Mars, the possibilities are absolutely endless. There are no concrete plans that have been made yet, largely because it is such a big project. And NASA doesn't currently plan to send people to Mars till the mid-2030s anyway, and there are innumerable things to focus on before then, like, for instance, how to transport the tons of equipment that are needed to set up a Martian base there, or even where we're going to build it. Those are the very questions that we're going to be discussing on Destination Mars next time. Thank you, meanwhile, to our contributors this week, who were Stanley G. Love, Paul Meacham, Ruth Bamford and Mark Wilson.
And now it's time for Question of the Week with Caris Lestrange. She's been busy answering Marco's question.
The Naked Scientist's Question of the Week, brought to you in association with the How to Wisman Foundation, supporting science and education from Alpha to Omega.
I was driving my truck, pulling a 53-foot trailer, and it blew over due to a strong wind. I was wondering if you could work out the wind speed so that I know when to stop driving.
Sounds like we've got some maths to do. I asked Zephyr Panoia, a PhD student at Columbia University, New York, to talk me through it.
So there's two things to think about here. How much force is needed to tilt the truck, and how far you can tilt it before it topples over.
So how does it create a force?
Well, air still has mass and density. It's pretty small, much less than water or metals, which is good because otherwise humans would all float on the atmosphere. But this means that when air is moving, it has momentum. Imagine putting your hand in a jet of water. As it hits your hand and slows down, you experience a force as the momentum of the water is transferred to your hand. So if we stop fast-moving air, for example when it hits the side of something solid, like a lorry, it will transfer momentum and there will be a force pushing the lorry over.
But what determines how fast the wind needs to be moving to tip the lorry over?
The wind isn't the only force. There's also gravity pulling down on the lorry, resisting the urge to tilt. For the lorry to start to lean over, the wind needs to be fast enough that enough momentum is transferred to overcome gravity. Once the wind gets strong enough, the lorry will shift over onto two wheels. And if the wind keeps blowing at the same speed, the lorry will topple. But if the wind drops off a little bit, so that the forces match again, the lorry can stay on two wheels indefinitely. Which is very cool, but it would be a little bit terrifying to see it coming along the motorway.
Oh wow, I imagine lorries driving on two wheels must be very unstable. Surely they fall over eventually.
Only if the wind speed increases again. Every object has a centre of mass, and as long as that is over its base, it won't topple. For most people, theirs is just behind their belly button. Think of your feet as a base. If your belly button sits above that base, you're stable. But as soon as you lean out, you start to fall. And that's actually what walking and running is. Overbalancing so that you start to fall in a direction, and then moving your legs fast enough to keep them toppling over. As soon as the wind has tilted the lorry enough that its centre of mass is on the wrong side of the two wheels, then gravity is now pulling the lorry in the same direction as the wind is pushing, and it will topple over. Probably quite spectacularly.
If you're a lorry driver, what could you do to stop your truck blowing over?
Well, if you can, fill it with stuff. The more you're carrying, the heavier the truck is, and the larger the force, and then higher the wind speed, is needed before you topple over. For an empty lorry, like the one Marco is driving, you can drive in winds up to about 60 miles per hour. But if you increase the weight with cargo, then you can manage much higher winds.
So, the speed you travel at isn't so relevant. It's how much your truck weighs and how large an area it presents to the crosswind that matters. Thanks to Zephyr Panoia for helping me answer Marco's question. Next week, we'll be tackling Stephen's question.
Are zombies feasible?
Crumbs, do you think there will ever be a zombie apocalypse? You can email chris@thenakedscientist.com, find us on Facebook, tweet @NakedScientists, or join the debate on our forum. That's nakedscientist.com/forum.
And that just about wraps things up for this week. Thank you very much to Greer Jackson for production. And if you have, meanwhile, any Mars-related questions that you would like us to answer, do please drop us a line to chris@thenakedscientist.com, or you can tweet @NakedScientist. That's because we'll be doing a special Q&A for our final edition of Destination Mars in 2 episodes' time. The Naked Scientist comes to you from Cambridge University. It's supported by the EPSRC, the STFC and Rolls-Royce. Goodbye from me and from the rest of the team.